All right, and so in the last video we talked about scalar line integrals, and but you're probably thinking, well, Professor Brett, we just talked about vector fields. Well, that's kind of the next question I have is, okay, well, if we think about integrating a vector field along a path, because we talked about a scalar function, right? So now we might have a vector field instead, and so, well, I want to kind of begin in the same way we did with the other video, and no, we don't have to do Riemann sums, but I kind of want to understand what this would mean. Okay, I'm going to define a path, right? It's a path. I'm going to define a vector field. Okay, great. And so my question is, what would the integral give? Okay, and let me get rid of this shade here. So I have just kind of a little sample drawing. I have a vector field and I have that path drawn in there. And so what I want us to do is stop for a moment and think. And I know some of the scenario I'm going to take might be aligned for some of you who are in physics, but I want you to think about a particle in space that is moving along this path, and it's traveling through this vector field. It could be a force field, so not like sci-fi force field, but like a region of space that has some force exerted on it. Or it could be a magnetic field, it could be a fluid, etc., etc. But there's some force being exerted on it. Okay, and so in some instances, the force could assist motion, or hinder motion. Wow, and this handwriting is terrible. Hinder motion. Okay, well, you get the point. So force could help or stop. Okay, and so what we want to do is determine how the vector field contributes to the movement of the particle. Okay, so i.e. to kind of measure the work. Okay, if the particle is doing work or if the vector field is doing work. Okay. And so to help us with this story, we still have this vector, so we still have that central question, but we are going to need to remember Tn and B from last semester. Well, we're going to talk about T, and that's going to be the unit tangent vector. Okay, and the idea here is that if we add up the dot products of the vector field with the unit tangent vector, well, here's the thing. Let me kind of explain what that would mean. Okay, even though I switched from being a astrophysics major to a math person, I still remember that work is force times distance. And now this isn't the whole story because these are both vector quantities and there's a dot product in there, right? So what we're actually doing by F with the dot product of T, so T really is that infinitesimal change in distance. Okay, if we want to think about it as an instantaneous rate of change at any given point, that's what it is. That's what D is. So that's why we want to add up the dot products, and so it's that idea of taking incremental changes over a small or over a large thing and adding them all up, just like the integral. Okay, so that's kind of the route that we're going to do. And consequently, when we do this dot product, remember that the dot product is giving us a scalar. Okay, so if I have to add up a bunch of scalars, this is starting to sound like, okay, we have a scalar function, right, f dot d, over a path. We just went through all that math. So guess what? We get to do it all again. Just kidding. I'm going to give it to you. Okay, so if we do this dot product, this is going to yield, let me get my colors going here, integral a to b f of x of t. Okay, and I need a vector symbol over that, and I'm going to dot this with the unit tangent vector x prime of t over the speed x prime of t, t length, and then I remember that I also have the speed hanging out here at the end. dt, and well, speeds end up canceling out. So for a vector line integral, all we have to do is a to b vector field restricted to the path. Let me write that again. X of t, and then dotted with the derivative of the path. And that's going to be our vector line integral. Okay? So, similar formula, just different application. We have a dot product since we have two vectors, and so we're going to get some examples in here quick. All right? So pause the video and read this if you need to. I'm just going to jump right in, and so I'm going to say that I'm going to end up getting 0 to 2 pi. All right, vector field composed with the path. All right, so I end up with negative sine t comma cosine t, and then derivative of the path. I dot that with this, so negative sine of t cosine of t. Hey, look, this is working out quite nicely because I just get integral 0 to 2 pi of 1 dt, which is just 2 pi. Great. Why does this make sense? I don't know. I want you to create a convincing argument to me and tell me the next time we see each other. I know I said that at the end of the last video. I want you to do it here too. Okay? One more quick example. Alright, so again, pause the video if you need to. I'm just going to dive right in. I'm going to say that this is going to be equal to, okay, we'll just write it out. Integral of the over the path of the field dotted with the derivative of the arc length is equal to, alright, 0 to 2 pi. And then I have cosine of t sine t, cosine t sine t, dotted with negative sine t cosine t dt, and if I add this up, this is going to be 0 dt, so I just get 0. Okay, and now here I want you to think about this physically too. Okay, so here our path is the unit circle. Okay, and I'm going to cheat and draw a unit circle with my special tool. Oh, that's not it. Okay, let's call that the unit circle. Okay, and per the parameterization, I am going counterclockwise. Okay, and that's per this t, right? And the vector field xy, well, that's just kind of going. If I look at these points, right? If I go at 1, 0, the vector field at 1, 0 would just be going that way, and similarly at all of these. And so, well, what do I know about the vector field dotted with the derivative of the path? Well, that's going to be 0 all the time. So that's the sort of argument that you should be making when we do something like this. So I would want you to maybe double check your reasoning with with what you have developed prior. Okay? So that's going to conclude this video, and we'll have one more video to wrap things up.